Alright, today we're going to take a look at the last section in our introductory unit that we've been going through. Now we're going to jump to chapter 3 and we're going to talk about solving what are known as linear systems. Now basically a linear system is just a combination of two or sometimes more than two linear equations. Alright, so we're going to look specifically at two different methods for how we can solve these. Alright, now before we get into the two different methods, which you can see on this particular slide, alright, one being elimination and the other being substitution, we've got to talk a little bit about when we are dealing with linear systems, more or less what it is that we are really finding or what we're really solving when we go ahead and solve these using algebraic methods. Alright, so like I said, key terms, substitution, and elimination, which we'll get into a little bit more here in a second. Now, if you think about having two linear functions or two linear equations that make up what we're going to call a linear system, if you were to graph those two linear equations or linear functions, you would get two lines similar to what you see on the right side of this particular slide. Now the thing you will notice here is that these lines intersect. Now they don't intersect in all cases, but in most cases your linear equations that make up your linear system are going to intersect. Okay, so basically what we're looking for is the point at which these lines intersect, which can be seen by the dot that I just drew up there. Okay, that is the solution to the system. Now obviously you could graph them and you could try to estimate where you think they intersect in terms of an actual point, but you can see based on the graph of these particular lines, they don't really intersect at what looks like a good point for us to estimate. You know, say I had a line up here and another line that came down through here, that would be a little bit easier because we could tell specifically that it intersects at the point 2, 4. And we wouldn't need to use an algebraic way of trying to calculate that solution intersection point because we could see it. Alright, as long as our lines were drawn, fairly accurately. When we have something like the point that I drew in earlier with the red and the blue line up there, we have something where we have to use a different type of method to tell specifically what the solution point for the system is going to be. Alright, so the first thing we're going to talk about is substitution. Alright, eventually we'll get to elimination. We're going to start with substitution, like I said. The thing about this is each method works best in a certain situation. There's going to be some cases where you're going to want to use substitution. There's going to be other cases where you prefer using elimination. It kind of becomes more of a case of what you're more comfortable with as you go through this. Alright, so this is what a linear system is going to look like. Alright, what we're going to do is basically, you can see up here we have two linear equations. Okay, linear because they have an x and a y in them, or two variables, and we have two unknowns because we don't know what x and y happens to be. Now what we're trying to do is figure out what x is and what y is based on what we're given here. Or more or less, if I were to take both of these equations on this particular slide, put them in slope-intercept form, I could graph them to see where they're going to intersect, and the point at which they intersect would be the solution. Alright, well I'm not going to go through all the trouble to graph them and see where they intersect. I'm going to use a different method. So what I'm going to do is I'm going to use substitution. So what I need to do with substitution is I need to pick one of the two equations up there, and I need to isolate either the x or the y, and then we're going to fill it into the other one in place of the x or y, and go ahead and solve after we get one variable in the entire equation. So that might not have made a whole lot of sense. It'll make more sense after I go through the example here. So I'm going to actually look at the top one here. Okay, and the reason I'm going to look at the top one is if you'll notice the x in the top equation, there's no coefficient on it, or there's no number in front of it. Alright, making it the easiest one to solve for a variable. So I'm just going to rewrite it over here. 2y plus x equals 4. Now what I'm going to do with that is I'm going to solve it for x. So essentially I'm going to subtract 2y from both sides, and I'm going to find out that x is going to be negative 2y plus 4. Alright, now what that does for me is it allows me to take the other equation that I didn't use, this one down here, alright, and in place of the x, I'm going to fill in negative 2y plus 4. Alright, so right here, like I said, in place of that x, I'm going to fill in 3, I'm going to go negative 2y plus 4, and then I'm going to leave the rest of the equation as is. Now you'll notice what happens is when I put that in place of the x, now I have all y's in that equation, so I can go ahead and combine what I can and solve for the y and figure out what the y component of my solution point is. Alright, one thing you have to be careful of is we use the top equation up here to solve for x. You cannot fill what we found to represent x back into the same equation that you used to start with, because everything will end up canceling out and it won't make any sense. Alright, so whatever equation you decide to pick from the beginning, like we picked the top one, alright, when I rearrange that and solve for one of the variables, like I did down here, okay, I have to take whatever I get or whatever I'm using as my substitution, and I have to sub it into the other equation that I didn't use. And again, the reason that we used the top one and solved it for x is because x was probably the easiest thing to work with because it didn't have a coefficient or it didn't have a number in front of it. So continuing on here, I'm going to distribute the 3. Alright, so I'm going to get negative 6y plus 12. I still have this minus 4y, and that's equal to 7. Again, the entire goal here is to solve for y now. Okay, so I'm going to combine the negative 6y and the negative 4y. Still have plus 12, and that equals 7. So if I subtract 12 from both sides, because I'm trying to isolate the variable, get negative 10y equals negative 5. Alright, last step would be I have to divide or do the opposite. Alright, and I'm going to end up with y equaling 1/2. Okay, now that's part of your answer. It's not your final answer. Okay, we figured out what the y is. We now have to figure out what the x is going to be that goes along with it. So what I'm going to do is I'm going to take this y equals 1/2, and I'm going to go back up here to our original set of equations, and I'm going to fill it in place of the y in one of the equations, and I'm going to solve for x. Now at this point, it does not matter which one of the two equations you pick. Alright, I'm going to pick the top one again, just because it looks like 1/2 will fit a little bit better in there. So if I take 2 times 1/2, which we're basically, again, just taking this answer here and filling it in for the y, plus x equals 4. Alright, again, I picked this equation because right here, this is going to end up being 1, or something that's fairly easy to work with. Okay, I can subtract that 1 back over the other side, and x is going to equal 3. Okay, so now I found an x and I found a y, and what you need to do is report your answer as a ordered pair, or something that looks like it represents a point. So again, what this does for us is this represents the point at which the two lines that were given, or the two linear equations that we were given, would intersect. Okay, so these do tend to get to be a little bit long because there's kind of some work that has to go into it. But as long as you remember your general process, okay, isolate one of the variables to begin with. All right, like we did here with the x. All right, we solved for x. All right, then we took x and we went back and we filled it into the other equation. All right, which allowed us to, with all this work over here on the left side, solve for y. Okay, once we solved for y, then we went back and we took the top equation, we filled that 1/2 in for y, and we solved for x. So we found an x value and we found a y value. Now that is substitution. I'm not going to lie, this probably is the method that I use the least. I tend to use elimination quite a bit more, but substitution works very well when you have a situation where you have a variable that is all by itself to begin with or doesn't have a coefficient with it. All right, then you can solve and substitution becomes a pretty viable option. All right, so what I would like you to do at this point is I want you to pause the video and I want you to go ahead and work through the problem that's on your screen right now. All right, so pause, come back, and we'll work through how we would go about doing this so you can kind of check your answer. All right, hopefully you had the chance to pause and work through what's going on here. Okay, so we're going to use substitution in a very similar manner to what we did on the previous slide. Now, again, substitution here, I'm going to take a look at the equation that has a variable that's kind of already semi-isolated to begin with. So I'm going to take that bottom equation because there's nothing in front of the y variable. All right, so I'm going to rewrite it, and I'm going to solve for that variable. So y is equal to negative 2x plus 2. All right, now we started with the bottom equation. All right, so what we're going to do is we're going to take what we just found that represents y, and we're going to fill it in for y in the top equation. So I'm going to rewrite that top equation. 5x plus, now in place of the y, we're going to put negative 2x plus 2, and that's still supposed to be equal to negative 9. Okay, so again, we filled in for y. Now we have all x's in that particular equation. All right, so I have to simplify and combine what I can. So I'm going to distribute my 6 here. So I'm going to get negative 12x plus 12, and that's still equal to negative 9. I can put the 5x and the negative 12x together, give me negative 7x. At the same time, just to kind of save some room, I'm going to subtract that 12 over to the other side. So negative 7x, which comes from this, is going to equal, looks like negative 21. All right, which is probably a good thing here because when we divide by negative 7, x is going to equal positive 3. Okay, so now I can go back up to the top and I can take my 3 that is supposed to equal x and fill it in. Now I'm going to go ahead and I'm going to take and fill it into the bottom equation again, even though we've already used that one, that particular equation more frequently than the top one. It just looks like the number is a little bit smaller, so it should be a little bit easier to fill into. So in place of that x, all right, I'm going to put a 3 plus y, and that's equal to 2. Okay, so I'm going to end up with 6 plus y equals 2. To solve for that y, get it by itself, I have to subtract 6 or perform the opposite operation. And y is going to be equal to negative 4. Okay, so again, I found both an x-coordinate and a y-coordinate that represent the point at which those two lines, if we were to graph them, would intersect. All right, so hopefully that is where you came up with the answer, and if it's not, hopefully you can see at which point you may have gone wrong. The other thing about substitution is, like we said, most of the time you want to use substitution in a situation where it's easy to isolate the variable. You can use substitution at any time you want. We could have even used it on this top equation if we wanted to. The problem is, as you can see, because you have coefficients of 5 in front of the x and 6 in front of the y, your answers are probably going to have some fractions in it, and they might not necessarily be the easiest to work with. So in those cases, it might be a better solution or better option to try using elimination, which we're going to get to here next. Okay, so elimination, I think after you get to using it, is actually easier to work with, but you kind of have to get used to what's going on. It's a little bit different strategy than when we were using substitution. Okay, so essentially with elimination, what we are trying to do, and it's explained on this screen fairly well, is we're trying to eliminate one of the two variables. So like with substitution, we only have x's or we only have y's left, so we can solve them. So what's going to happen here is essentially we're going to take our linear system and we're going to kind of add them together up and down in an attempt to try to get some of the variables to cancel out. Now sometimes it's going to be set up to work that way to begin with. Other times we might have to multiply an entire equation by a certain number in order to get something that's going to work out for us. Okay, so if we look at this particular equation, and this one's one of those that's kind of set up already for you, what you'll notice is you have plus 2y up here, you have minus 2y down there. They are opposites. All right, the whole idea of elimination is we want to take our two linear systems and we essentially want to add down, okay, or add them together, almost like combining like terms right on top of each other. All right, well in this case, because you have a positive 2y and a negative 2y, when I add down each of these three columns, like the first case here, I get 7x. When I add down this second one, you can see that the y's are going to be gone, and I'm just going to be left with negative 14 when I add the 4 and the negative 18. Okay, essentially, without having to substitute anything, I took care of eliminating the y's. Now, dividing both sides by 7, I get x equaling negative 2. All right, so we've saved a lot of time already with this particular one because it was set up to work for us already. Now, just like the last one, once we figure out one of the components of our ordered pair, in this case the x, we have to go back and we have to fill it into one of the equations. And in this case, neither one of them really look like they're any easier to work with than the other. So I'm going to take the top one, and in place of that x, I'm going to put in negative 2 plus 2y is going to equal 4. So again, my whole objective now is to solve for the other variable that I didn't already solve for. All right, so I'm going to add 6 to both sides. I'm left with 2y equaling 10, and we're multiplying 2 times y, so I will divide by 2, do the opposite, and y is going to equal 5. All right, so what you'll notice about this is we still arrive at an answer, all right, or a point at which these two lines would intersect if I graph them. All right, but in this case, it was probably a little bit easier to get to that particular solution because of the way things were set up to begin with. Now, the thing that you'll see here as we move to the next slide, before I give you a chance to work on one, is they're not always going to work out the way this one did, in terms of having, you know, a positive 2y and a negative 2y in this case. All right. In some cases, like you'll see on this particular slide, you will notice that I have 3x and 2x, and I have 5y and 3y. So if that's the case, what we have to do is we have to think about, I'm going to have to multiply the entire top equation and the entire bottom equation by a number in order to get things to match up like they did for the y's on the last particular slide. Now in this case too, what I'm going to change up is I'm going to try to get rid of the x's. So what I'm going to do is, if you notice, we have a 3 in front of this x and a 2 in front of this one. Okay, so what I'm looking at is trying to think about what numbers do 2 and 3 go into, okay, or more or less what's a multiple of 2 and 3, which would be 6. So I want to think about, I want to multiply the top equation, the entire top equation, all right, by 2, both sides, everything involved. And I'm going to take the bottom equation and I would multiply it by 3. Now the other thing you got to remember is we have to get opposite signs. So I'm actually going to make that a negative 3 when I multiply by there. So I will get a negative 6 in front of that particular problem. So what's going to happen here is, because I multiplied everything in each equation by the same thing, the top equation by 2, the bottom equation by negative 3, I really haven't changed the value of anything. I've just changed the way that it looks, which is going to help me out in the long run here. So I'm going to perform all that multiplication. So the top one, I'm going to get 6x plus 10y, because I have to multiply the 5y times 2. And on the other side, I'm going to get negative 32. When I multiply the bottom one, I'm going to get negative 6x minus 9y equals positive 27. Okay. Now again, you just have to be careful. Sometimes we tend to forget about these middle terms because we don't have the 2 and the negative 3 written next to them. Just remember, you're multiplying everything in that equation by the numbers that you deemed appropriate to begin with. Alright, so again, the entire goal of this was to get the 6x's, or the x's, to cancel out, which they do. Alright, so now I'm looking at y equaling -5 when I add up and down each column. So that worked out fairly well. So now what I need to do is I need to take that -5 and go back and fill it in. Now here's the deal. You can go fill into either one of your original equations, or if you wanted to, you technically could fill in to one of the equations that you manipulated and found by multiplying there. Now the thing about that is usually the numbers down here tend to be a little bit bigger, so it usually is easier to go back to the very beginning. So I'm going to go back to the beginning, and I'm actually going to use this equation on the bottom. So 2x plus 3 times -5 is going to go in there for that y equals -9. Okay, so 2x minus 15 when I do the multiplication still equals -9. And when I go ahead and add the 15 to the other side, I get 2x equal to 6, positive 6, divided by 2, divided by 2, and x is going to equal 3. So again, I found a solution point, which in this case would be 3, -5. All right, now, if you happen to be a little bit worried that you're not sure whether or not that's the answer, what you can do is you could take 3 for x and -5 for y, and you could fill them into your original two equations up at the top here. And what should happen is when you fill 3 in here and -5 in here, this side should be equal to 16 or -16. And the same thing would happen with the bottom. But it would have to work for both equations in order to be true. Okay, so again, that's one way that you can check to make sure that your solution point really is a solution point to that particular system of equations. All right, now here's your chance. Again, I want you to pause the video and I want you to work through this particular problem using that elimination strategy to see what you come up with. All right, and then you can come back and we'll work through the answer together. All right, hopefully you had the chance to work through this, and hopefully you came up with a solution point that looks like it could be a possible answer. We're going to use elimination, so what I would do here is I'd probably focus on the y's just because they're smaller numbers. So what I would do is I'm going to take the top times 5, and I'm going to take the bottom times 3. Now I don't have to involve any negatives here because you can see that we already have opposite signs in the middle here. So taking the top times 5 and the bottom times 3 will get us to where we need to go. Okay, so when I do that, on the top, I'm going to get 25x minus 15y equals, that one's going to be a little bit big, you better pull out the calculator and try to figure that one out. 42 times 5, it's going to be 210. Alright, and then when we multiply in the bottom, we're going to get 24x plus 15y, which is good, and 28 times 3 is going to give me 84. Alright, now you can see with this particular problem, some of the numbers get to be a little bit big. That's okay. If you need to use your calculator, go ahead and do it. I'm going to take 25 plus 24x, and I'm going to get 49x. Now you can see here the y's are going to cancel. So 49x is going to be equal to 210 plus 84, which is 294. And then if we were to go ahead and divide by 49 to get that x by itself, you're going to get 6. So x is equal to 6. So don't let those big numbers fool you. You're still going to get a fairly easy number to work with. So now what I'm going to do is go back to the beginning like we talked about, and I'll take the top equation, and in place of that x, I'm going to put a 6, and I'm going to use that to try to figure out what my y is going to be. So 30 minus 3y is going to equal 42. I have to subtract 30 from both sides. So negative 3y is going to equal 12, positive 12, when I add that 42 to negative 30. Divide by negative 3, and y is going to equal negative 4. All right, so 6, negative 4 is my solution point. All right, and again, if you wanted to check and go fill that in to both equations, it should work out in both cases that 6 and negative 4 give you the solutions that it said it should up there. Okay, now one other thing I have to talk about here, and then we'll get to a story problem, is just the fact that it is possible for systems to have no solutions or possibly many solutions. And the whole idea is, we've talked about from the beginning, with solutions or systems to solutions, we're looking for the point at which lines intersect. That has been our solution to this point. Well, it is possible that you could have two lines that make up a system that are parallel. Okay, when they're parallel, you don't have any solutions because those lines don't intersect. And it is possible in some cases to have a line and then just kind of have another version of that line that's written right on top of it. Or the equation of that line gives you a line that happens to be the same as the other line that was there. Okay, now obviously if you were graphing, you'd be able to tell whether or not you have parallel lines or whether or not you have the same lines. When you're doing things algebraically with substitution and elimination like we've been doing, there's specific things that happen while you're solving the problem that you have to look out for to let you know that you have many solutions, or you basically have the same line on top of the other line, or you have no solutions in which you have parallel lines. Okay, so again, parallel lines in the case of linear systems means you have no solutions, okay, which would be a contradiction like it talks about down here. If you have the same line, or basically one line and the other line would be graphed on top of it, think about it as intersecting in an infinite number of places, all right? And that would be referred to as an identity. So when you're solving linear systems, if you ever get all your variables and your numbers to cancel out and you end up with 0 equals 0 at the very bottom, that means that you have an identity, or basically those lines represent the same line. If you ever get everything to cancel out in terms of variables and you get something like 1 equals 3 on the bottom of your particular solution, obviously that doesn't make any sense, and that represents a situation in which you have parallel lines that never intersect, therefore have no solution. So we're going to run through an example real quick of what this might look like. Now, once we get to this point, I don't really care what method you use to try to solve these. If you want to substitute, great. If you want to eliminate, fantastic. Okay. In this case here, I am probably, like I said before, I'm more prone to using elimination, but I'm going to use substitution for the simple fact that right here, this one's going to be fairly easy to rearrange. So if I take that top equation and I rewrite it, and then I solve for the y, you'll notice that I'm going to get y equals negative 3x plus 1. Okay. My other option with that would have been I could have multiplied the top equation by negative 6 all the way across and gotten a new equation that would have got the x's to cancel out. But I opted for this one, and so we'll roll with that instead. Okay, so I'm going to take the bottom equation now, the one that I didn't fill in for, and I'm going to fill negative 3x plus 1 in for my y, plus 6x equals negative 18. So over here, I'm going to get negative 6x plus 2 plus 6x equals negative 18. All right, so you can already see in this particular situation right here, my 6x's are going to cancel each other out. So I'm left with 2 equal to negative 18. Well, 2 doesn't equal negative 18. So what you have here is a contradiction, which we would also represent by saying no solution, or you would have to say that these are parallel lines. Okay, they're never going to intersect, therefore you're going to have no solution. Now you can also see up here, had I taken the top equation times negative 6 all the way through and gotten, well, let's see, do I want to do that or not? I'm not going to worry about that so much right now. We could have, I guess, what the heck, negative 18. Well, no, I'm not. I'd have to do some rearranging because you'll notice how the x's and the y's are not on top of each other like they were before. So originally when I said multiplying the top times -6, that's not going to work because I didn't have it written in the correct order. What I wanted to do is I'd want to make sure that I had the 6x under that and the y under there before I decided which particular numbers I wanted to use to eliminate. So in this case, that also makes substitution a better option as far as what's going to happen. Now, if you would eliminate, what you would notice is all the variables would essentially cancel each other out, and you'd be left with like 0 equals some number on the other side. And you would have essentially arrived at the same solution. So just be aware of things like that that can happen as you go through. If you get a number equal to another number, say for example 0 equals 0, you have infinitely many solutions, or basically both equations that would be there represent the same line. Or you can end up with a situation like we did here by substituting. We end up with 2 equals -18, or in some cases you'll end up with different numbers like 1 equals 3 like we had on the previous slide that represent what's going on there. Okay, now very last thing we need to talk about is there are a couple story problems that go along with this, and we've been working on linear systems, so that means we're using linear systems to solve this particular equation. So what we have here is a veterinarian needs 60 pounds of dog food that is 15% protein. He will combine a beef mix that is 18% protein with a bacon mix that is 9% protein. How many pounds of each does he need to make the 15% protein mixture? All right, so what we need to do is we need to come up with 2 different equations that we can put together in a system and use to solve this. All right, now our first equation is basically going to be pretty simple, and this is the way it works most of the time, is we have, we need to get 60 pounds of dog food. And there's essentially 2 different things that we're mixing together. We have a beef part and we have a bacon part. So we're just going to write that like this. Okay, if you add those 2 together, you should get 60 pounds. All right, then things get a little bit more complicated as far as what each one is supposed to be made up of. Okay, so we want a beef mix that is 18%. So I'm going to say 0.18 times x plus we want a bacon mix that has 0.09 or 9% times y, and that's supposed to give us something that is 15% of, or 15% protein, or we're trying to figure out basically how much protein would be involved with that particular mix. All right, now you can see on the right side there, you have 0.15 times 60, so you can actually combine that, and that's going to end up being 9. Okay, so I'll just write that there in the end. But again, I'm back to a situation in which I have 2 linear systems, and I can go ahead and solve for one of the variables in order to get to the other variable. All right, now in this case, I would say your best bet would be to probably don't try to eliminate with something where you have decimals on the bottom. Just take the top one and either solve it for x or solve it for y, and then you can fill into the bottom and go from there. So for example, well, let's just say we take the top one and we're going to solve it for x. So x would equal -y plus 60. So then what I would do is I would take, in place of the x on the bottom, so I'd go 0.18, and in place of the x, I'm going to put -y plus 60. I have plus 0.9y, and that's supposed to equal 9 after we do our calculation. So I'm going to get -0.18y plus, probably going to need a calculator to figure out what this is supposed to be, but 0.18 times 60, 10.8, plus 0.09y is going to equal 9. Okay, now we got a little work to do here. -0.18y plus positive 0.9y is going to give me negative, I'm going to write this over here because I'm kind of running out of room, 0.09y. I can subtract the 10.8 to the other side. All right, which is going to leave me with negative 1.8. All right, and then we would just have to do some dividing there, and you can see this is actually going to work out fairly well, because when I divide both sides by negative 0.09, I'm going to get positive 2. Okay, now obviously, if I get positive 2 in this case, you should be able to tell fairly easily that the equation that I want to go back and fill into is probably the top one, because I'm not going to want to try to fill into something that's decimal. So if I would take the 2 and fill it in place of the y here, you can see I'm going to get 2 in that place. I would have to subtract it over the other side. So x is going to end up equaling 58. All right. So that just tells you how many pounds of each particular mixture you would need. In this case, you would need 58 pounds of the 18% mix and only 2 pounds of the 9% mix in order to make this work. So technically your solution is still a ordered pair as far as what we're trying to do. Okay, so hopefully you had the option, or not option, but you had the chance to take some notes, write down some different examples that we went through on here. If you do have any questions, please make sure you ask. Otherwise, just make sure you come to class ready to go as far as some questions that you might have, or hopefully you're able to work through and get through most of the material in the assignment.